I'm Chen from the University of Michigan. I'm happy to share our exciting work on a novel method for incremental spectral clustering of increasing orders. This is a joint work with my collaborators at IUPUI, Baizhen Zhang and Professor Mohammed Hassan. Professor Hassan is also in the room. This is also a joint work with my advisor, Alfred Hero. Since this is a great workshop that focuses on graph mining, I don't think I need to spend any time to convince you that graphs are common and useful presentations of many data. And most often, we are using a lot of matrix decomposition techniques to do graph mining. Before I introduce our methods, I want to show you two motivating examples of why we are interested in this incremental eigenpair computation problem. So the first example is actually interactive graph data mining, especially for graph clustering or community detection problems. So one of the known problems for community detection is that we don't know what's the number of communities that we want to know at the first place. So as a data analyst, you may want to ask the graph mining algorithm to give you, let's say, 5 communities at first place, and then it will provide you all sorts of. Seems like there's some scalability issue here. It will provide you some all sorts of clustering metrics like modularity, like the distribution of the cluster sizes. And then if the user turns out to be not happy with the current clustering results, it might go back and ask the algorithm to give me, let's say, give me 6 clusters instead of 5 clusters. And in this case, there are some like recomputation or incremental computation needed in this for this algorithm to speed up the incremental process, because you already know the information that you need to compute the first 5 communities. The second intuition is from our recent work on automated model order selection for community detection. So we have a nice new clustering quality function that measures how well a clustering results are, and it also provides statistical reliability analysis in terms of p-values and confidence intervals. And one of the process in our algorithm is that it needs this iterative graph partitioning, starting from partitioning the graph into 2 clusters and then 3 clusters until it finds the minimal number of partitions that meet this robust or reliable clustering criterion. And you can see there are 2 examples of internet map between North America and Europe, and you can see that the clusters that automatically found by our algorithms match the geodesic separations of the locations. Based on these intuitions, we would like to have a nice incremental eigenpair computation methods that can enable us to do fast and efficient eigenvalue computations. Particularly, we will focus on graph Laplacian matrices, because graph Laplacian matrices are affiliated to a lot of graph problems. For example, the smallest eigenvectors are known to be the solution of the relaxed graph cut problems. Let L be the graph Laplacian matrix, and then if you consider a normalized graph Laplacian matrix, that will be the weighted degree matrix minus the weighted adjacency matrix. And then we use lambda I and bi be the smallest eigenpair of the graph Laplacian matrix. So how spectral clustering works to do community detection or graph clustering is just use its k smallest eigenvectors and then do a k-means clustering on this low dimensional representation to get k clusters. So what we are able to show is that if you are given the originally computed k smallest eigenvectors, how do you compute the next k plus 1 smallest eigenvector? All you need to do is to construct a matrix L tilde, and then you run a power iteration on this L tilde, and then the leading eigenvector, the largest eigenvector of L tilde, will be the next eigenvector that you need to do this incremental community detection. And we have the analytical expression for this L tilde is nothing more than a function of the original graph Laplacian matrix L, and then the originally computed eigenvector matrix Vk, and also the graph connectivity properties like how many connected components you have in the graph. Let's zoom in to see what's the advantage of this method that we call incremental I/O, incremental eigenpair computation with increasing orders. So the first advantage is that it's very efficient, because all you need to do this incremental computation, it all boils down to a power iteration method, and then we all know that power iteration converges pretty fast. And then it's also very general because this L tilde it all fits into different varieties of graph Laplacian matrix. For example, it fits to a normalized and normalized graph Laplacians, and then for disconnecting and connected graphs. It's also very adaptive if you want to do a blockwise update, meaning you want to compute the next, let's say, next 3 eigenvectors instead of compute one eigenvector at a time. It can be easily adapted following the same methodology. So let's show some numerical results. We generate a synthetic graph from those Randy graphs, and then we try to compute the smallest eigenvectors of the graph Laplacian matrices from k equals to 1 to k equals to 10 eigenpairs. And there are 3 curves in this plot. The blue one is the batch method, which is regardless of the previously computed eigenvectors. It just do a batch eigenvector decomposition from scratch for each increment in the eigenpair. And the black line is the Langzow's method for increasing orders. Oh, sorry about that. Yeah, but they say it's not effective. Okay. So the black line is the Langzow's method. So Langzow's method is originally designed for a fixed number of eigenpairs by computing the Langzow's vectors. So Langzow's IO, what Langzow's IO does is that we incrementally compute the new Langzow's eigenvectors and hope that you will give a good approximation to the additional eigenvectors that we want to compute. And then the red method is the incremental method that we propose. It's called incremental IO. So you can see that the left figure is the number of eigenpairs compared to the running time. So you can see that incremental methods like Langzow's IO or incremental IO, they are linear in terms of the number of eigenpairs. And it makes sense because we just show a theorem that shows that for each increment in eigenpair, it's just like a power iteration like computation. So it's really linear in a number of eigenpairs. And what's good about this incremental methods is that if you look at the right figure, that comparing with the number of nodes, it shows like a log linear behavior, which means that the computation time is like a grows with log n. And the last thing we want to do is show is that although in the synthetic data, it seems like Langzow's IO and our method has similar performance, but in reality, if we compare the eigenpair computation, incremental eigenpair computation for the 6 real-world data sets, it actually shows that our method is more robust and consistent than the Langzow's method. So you can see the left figure is the time difference between the batch method and our proposed method. So you can see that our method is consistently better than the batch method for all data sets. And if the number of eigenpairs if the number of eigenpairs is larger, then the time improvement is better because the incremental method actually saves you more time. However, the right figure shows the time difference between the batch method and then the Langzow's method. So you can see Langzow's method is actually not so robust. So among 4 out of 6 data sets, Langzow's IO actually has worse performance. Worse performance means like more computation time needed than compared with the batch method. So our conclusion is that incremental IO is more consistent and robust because of this power iteration nature, whereas the Langzow's method, although it's pretty known for like a fixed eigenpair computation problem, but in terms of incremental computation, it's not so robust. So our conclusion is that we propose the incremental eigenpair computation method that is fast because of power iteration. It's robust in terms of the real-world data, and then it's easy to implement because it's a methodology that does not compromise to any performance loss. And it can be applied to different kinds of graph Laplacian matrix for disconnected and connected graphs. We can show a nice significant improvement in terms of computation time. And finally, the codes for how to implement our codes and then the comparison between the Langzow's method are available at the website. And thank you, and happy to take questions.